Okay, so welcome. It is January 20th, and this is Psych 222. Today we're going to continue talking about matrices a little bit, and then we're going to get into the fundamentals of calculus and review a few of the concepts from introductory mathematics. And again, we're doing this to prepare ourselves a little bit for what's coming up next week, because next week on Monday, we are officially into the book. So that's what we're doing this week, is still reviewing a few of the fundamentals. Now, not all of this stuff are we going to use immediately when we get into the actual book, but you should be familiar with some of this background. And if you haven't seen some of these things before, that's perfectly okay. As you notice from the appendix is very long. We could easily take that appendix and study it for an entire year. Okay, just that appendix, we could study it for an entire year. So you don't have to know anything close to all of that appendix. All you do need to know is some familiarity with the topics we're talking about and work on the exercise questions. So when you're studying for the course, it's really good to focus on those assignments, because that tells you what is most important to know from the course. Okay, make sure you don't get overwhelmed by looking at this whole appendix and figuring the course is going to be extremely hard, because it won't. And as we get into the book, you'll see it actually, we actually lighten up a little bit because it's not quite so technical, at least at the beginning. On the other hand, if you do have a bit of a background in mathematics, then you're strongly encouraged to look at this appendix in quite a bit of detail, because if ever you decide to go into data science, machine learning, or any kind of quantitative area like that, you have to know all this. So all the stuff in this appendix you should be familiar with. And if you do wish to go further on into statistics, applied statistics or theoretical statistics, stuff in this appendix is going to be necessary prerequisite knowledge. Okay, so let's continue talking a little bit about matrices. And we mentioned last time that a matrix, I've drawn one over here, a matrix can be considered to be a container of numbers, right? It could be considered to be pasted vectors together. So there's the matrix A, and I have how many rows and how many columns? Well, I have 3 rows, right? 3 rows to the matrix and 3 columns. Now, what are these things in the matrix? Well, these are elements of the matrix. And in this particular case, these are simply numbers. I just put some numbers in there. Now, when you're working with matrices mathematically, sometimes the pure mathematician doesn't really care what these numbers represent. They can simply be numbers. But as a scientist, right, as a scientist, you care what those numbers represent, of course. And what might they represent? Well, maybe they represent data on different variables. So maybe I have verbal scores, quantitative scores, and analytical scores on some IQ test or something like that, right? So this would say that this is the verbal variable, and this person's score is 3, this person's score is 1, this person's score is 2, etc. So you can see that the matrix serves as a nice container for the data. And when you work with spreadsheets, when you work with Excel and other software, you're always dealing with matrices, because when you look at your software grid, all of that could be considered one big matrix, right? So when we think of matrices in terms of data, it's really not that mysterious. It contains numbers, and those numbers are often considered to be data. Now, what's all this stuff, right? All this stuff is just mathematical things we can do with matrices. So when we say things like C times A, where C is a constant, is equal to A times C, and we call that the commutative property, all this is saying is there's a property of matrices that we can take C times the matrix, and it's equal to A times C. And these are useful properties to have, because if you do further work with matrices in mathematics, you need to be familiar with the rules of the game, so to speak, that you can work with matrices in this way. Okay, that's all that is. Now, I want to make sure that as we go through this, you're trying to demystify these things, right? Sometimes we think of mathematics is very, very complicated and over our heads and things like that. But if you understand what mathematics is about, then you'll still see the complexity of it. It'll still look sometimes intimidating, but you'll understand what's really there, right? And then it loses its mystery quite a bit because you see what's going on, okay? So for instance, this one right here, 0 times a, well, that's equal to 0. And that's just like in ordinary algebra, because if I take 0 times x, well, that's equal to 0. So this is not anything complicated. It's just a property that you can work with matrices that way. Similarly, look, if I multiply the matrix by -1, I get a negative matrix. That's no problem, because that's the same thing we would have if I had -1 times just a variable in ordinary algebra. So that would equal -a. And we can go on and on with properties. So that's all we're dealing with there. Now we want to talk a little bit about the inner product. Okay, so the inner product, sometimes called the dot product of two vectors. Okay, remember what a vector is. Any one of these columns or rows could be considered a vector. So if I wrote that first one out like this, 2, 1, 3, well, there's a vector, right? There's a vector. I could also write a row vector. So I can have 3, 1, 6. There's a row vector. So we want to talk about the inner product, or also called the dot product, of two vectors. So it's a product of two vectors, each with the same number of entries. So each with n entries. So we have 1, 2, 3, n equals 3, 1, 2, 3, n equals 3. And we also know that the transpose of the matrix is taking it from a column matrix and putting it into a row matrix. So A transpose times B is a scalar, so it's a number formed by multiplying corresponding entries of the vectors and summing the resulting products. That's what the inner product is. So let's look at the abstract notation for it. What this says is take the transpose of A and multiply, that dot means multiply, times the B matrix. Now in summation notation, start with the A sub I element times the B sub I element. And which elements are we starting off with? Well, we're starting off with the first element right here. That's what the I means. When you read summation notation, this I equals 1 means start with the first element. Now, if that said I equals 2, then that would mean we're starting with the second element in our data. Okay? Usually that's going to read I equals 1 because we usually do not have a good reason for saying I equals 2. And we're going to sum up to the nth observation in our data. Now, this is called summation notation, and it's going to play a pretty big role with when we get into the book starting next week. We're going to see a lot of summation notation. So this serves as a good opportunity to review that notation if we've never seen it before. So here's two vectors. There's one vector. There's the multiplication sign, and I'm going 2, 0, 1, 3, negative 1, 6, 0, 9. So the inner product says multiply those pairs. 2 times negative 1, 0 times 6, 1 times 0, 3 times 9. And I'm adding those. There's the summation, right? See, that's the summation reflected in adding those terms, right? I'm adding those terms until I get a number of 25. And that's called the inner product or dot product of these two vectors. Okay? And inner products are used heavily in statistics, especially in more advanced courses. And it's something you should know if you plan on going into stats in those areas. Two matrices A and B are conformable for multiplication if the number of columns of the left-hand factor, so that's A, is equal to the number of rows of the right-hand factor. Now, this takes a little bit of explaining. What do we mean by conformable for multiplication? Well, we know that if I take A times B in ordinary algebra, right? If I say I have variable A and a variable B. Well, this is equal to B times A, right? So if I take a number here, -3 times 2, well, that's equal to 2 times -3, right? Notice I could just switch those around. When you talk about matrices, the key here is AB does not usually equal BA, okay? The matrix product A times B is usually not the same thing as B times A. So when we take two matrices and we say they're conformable for multiplication, we have to have the condition that the number of columns of the left-hand matrix is equal to the number of rows of the right-hand matrix. So look at these two matrices over here. They're simply two arbitrary matrices. Number of columns of the left hand. Well, how many columns do we have? 1, 2, 3, right? We have 3 columns here. How many rows do we have here? 1, 2, 3. Therefore, these two matrices are conformable for multiplication because this condition is satisfied. Therefore, we can multiply these two matrices. They are allowable to be multiplied. Now, what that means is if they are not conformable for multiplication, they cannot be multiplied. Look at these two matrices, right? How many columns do we have? 1, 2, 3. How many rows? 1, 2. Not conformable. I cannot multiply those matrices. So in the land of matrix algebra, these matrices cannot be multiplied. We need to satisfy that conformability condition. So we can write this more generally as this, that when you obtain the elements of a new matrix C, well, this is how we're going to multiply it. So you're going to multiply the column and the row for the given values of the variable. Now let's look at, it's much more enlightening if we look at an example to see how this works. You're going across the first row and down the first column. So for the first one, I'm going 1 times 1 plus 2 times 0 plus 3 times 0. What does that look like? That looks a lot like the inner product that we just discussed, right? So we're seeing that when we multiply matrices, what we're actually computing are a whole bunch of inner products. Look at the second one. Let's go down to this one right here. Across here and down here. So what do we have? 4 times 0, right? 4 times 0, so there it is, plus 5 times 0, plus 6 times 1. And you can do all of those elements in the multiplication, and this is the matrix you get, okay? That's an example of multiplying matrices. Do you have to memorize it? No. You just have to know that matrices have to be conformable for multiplication. Computers are going to do the work for us, right? When they multiply matrices. Guaranteed that on your computer right now, the video you're viewing is performing matrix multiplication and transferring information and computing new things. So these are very small matrices right here, but you can imagine, just imagine what your computer is doing, right? And that's what computer scientists study is, imagine you have 1,000, right? 1,000 rows and 1,000 columns, and it has to multiply by another matrix with 1,000 rows, 1,000 columns. Those computations are huge. So when you think about what your computer is actually doing, when you enter a command and things like that, it's really, really amazing because it's making a whole bunch of computations on things that would take forever if we were to do it by hand. But still, it's useful to see how it works. Here's another example that we are going to see this when we get to regression analysis later in the book. I'm going to take these values and I'm going to multiply by these. Well, there's b sub 0 times 1 plus b sub 1 times x1, etc. And I multiply that through. Now, what these represent, we don't know yet, but we're going to see when we get to regression what these types of coefficients represent. But the point is that we need to be able to do multiplication in order to work with statistics. Some other properties of multiplication, we have associative and distributive. Here's a distributive property right here. A plus B is equal to AC plus BC. And we see that distributive property, right? Remember when you distribute, you're taking AC plus BC and so on. But it's generally not commutative. Now that commutative property is what we just talked about, right? We said AB is usually not equal to BA. So that's that important property. So this may be defined, but this may not be defined, okay? If that equal sign does stand, so if we don't need that bar through it, then we say they commute with each other. But what we just said above is AB does not usually equal BA. So we say that matrix multiplication is in general not commutative. And that's the point we just made. A few other properties here. Well, we can take the identity matrix and say A times the identity matrix is equal to the identity matrix times A, which is equal to A. Remember, we said that the identity matrix serves as the number 1 in matrix algebra. So that we're getting this result is not surprising. A times 0 is equal to 0. 0 times A is equal to 0. Again, these are just properties of matrices for multiplication. And there's nothing complicated going on here. We're just noting that when we multiply the matrix by 0, we get 0. When we put 0 first and multiply by A, we get 0. Okay? Demystifying the mathematics. That's what you're trying to do, is look at and say, that's actually pretty simple. Okay, let's skip the powers of the matrix, not necessary. I'm just going to skip behind there too so we can move on. So you can read this over if you want, the sense behind matrix multiplication, but we want to keep moving on. I want to talk about matrix inverses. We remember from ordinary algebra that if I have, say, 6x, right, where x is a variable, and I say it's equal to 12, well, we know that we can solve for x, right? 12 over 6 is equal to 2. That's no problem, right? And what's going on here? Well, where 1 over 6 can be written as 6 to the negative 1, right? 1 over 6 is equal to 6 to the negative 1. We can write it in both ways. So when we talk about inverses in matrix algebra, we need to kind of simulate this idea over here, where we have this kind of like multiplying by its inverse. So what does the inverse mean? Well, let's take a matrix here. So this matrix is 2, 5, 1, 3. Now, the inverse of this matrix, okay, the inverse of this matrix, okay, is equal to this over here. Now, why would we say this is the inverse to this matrix right here? Well, what did we say up here when we were looking at the 1 over 6? We said this is the scalar inverse of 6, right? So 1 over 6 is the inverse of 6. So whether we write it as 1 over 6 or we write it as 6 minus 1, that's the inverse of 6. Why? Because look, 6 times 1 over 6 is equal to what? 6 over 6 is equal to 1, right? So we see that 1 over 6 is the inverse. Well, look at what we do when we work with matrices. If you trust me for a moment to say that this is the inverse of this matrix up here, then what should be true? Well, what should be true is if I take this and multiply it by this, I should get what? The corresponding 1 matrix, the identity matrix. And that's exactly what we got up here when we were working with the scalars, right? With ordinary numbers. Notice we got the 1. So the idea of matrix inverses is exactly the same as this simple idea we have up here. It just looks more complicated because we're dealing with bigger numbers and matrices. But other than that, the concept is identical. So 2513 times this thing right here is equal to what? The identity matrix. This is the identity matrix. That's that number 1 in ordinary algebra. That's how we can say this is the inverse to this. Okay? And we could also take that inverse and multiply it by the original matrix, and we get the same thing. So when we think about inverses in matrix algebra, we just mean what's that matrix that we can multiply the original matrix by and get the identity matrix. Now, how this is achieved requires a lot more explanation than we have time to go through. And it requires looking at an algorithm as to how you get the inverse. But for our purposes, all we need to know is that we can get an inverse, and what it means is to get that identity matrix when you multiply those two. Okay. Okay, let's continue on here a little bit. We skip determinants, skip that. I think we are pretty much ready to get into some calculus. So like I say, if you plan on going on into further math or stats and you want to go heavily into data science and things like that, you should read some of this stuff. This basic vector geometry is very, very useful, and some of it will be a review of things you've seen before. But all of this stuff is really good stuff to have if you plan on going further in stats. So let's get to discussion of calculus. I'm almost there. There we go. Okay, so what we've talked about in Appendix B, we've talked about a few elements of matrix algebra. Now we're going to talk about calculus. And like I say, many of you have had algebra before. You may have studied those matrices a little bit. That may look familiar. Some of you definitely have seen that stuff before. You may have even learned some of it in high school. And a lot of you have probably had some calculus in your past. High school, maybe the first year calculus course. And what we want to do here is just talk a little bit about what calculus actually is. Why do we do calculus? Calculus is seen as one of the biggest inventions in the history of science. So it's really, really important. A lot of things that scientists do today are due to understanding calculus. If it wasn't for calculus, a lot of the things we do, we just wouldn't be able to. And that includes, launching shuttles into space, developing computers, and all kinds of technology. So calculus is really, really important. You can read the intro there if you like. To get to calculus, we need to talk a little bit about the fundamentals of math. And one fundamental is that of a straight line. So we know what a straight line is. This looks familiar. Y equals A plus BX. Well, A is the intercept of the line, and that looks familiar. And X is the input here, and B is the slope. So there's the slope of the line, B, and A is the y-intercept. Now, why do we want to compute lines? Well, we're going to use lines in statistics all the time. So when we get to a technique called regression towards the end of the course, we are going to be dealing exclusively with lines. Okay, let's look at different possibilities for the slope. Well, there's a slope greater than 0. Line is moving up. And there's a slope less than 0. The line is moving down. And there's the flat slope over here. Notice something about this flat slope idea. Notice that if I increase x, right, as I have an increase in x, what happens to y? Right? What happens to y? Nothing, right? As I increase x, nothing happens with y. So if I go from here to here, I've got a change in x, but I have no change in y. Nothing's happening. If I look over here, I'm not going to deal with the negative one. If I go over here, if I have a change in x, what do I have in y? I have a change in y, right? Change in x corresponds to a change in y. So to denote change, how about I just do this? Delta x corresponds to delta y. Change in x corresponds to a change in y. That rate of change, right? That's a rate of change, is called the slope. So when I change a unit in x, how much do I change in y? And if I change 1 unit here in x, and I get a corresponding 1 unit change in y, well, then I have that slope is equal to 1. Now, in some cases, I may have a very steep slope. So a certain change in x corresponds to a much larger change in y. Notice the change here, delta y and delta x. In science, we're always interested in rates of change. Okay, science is about rates of change. Let me give you an example. We will be talking about COVID-19 throughout the course, especially when we get into the book. We're going to be talking about COVID in almost every example. But what's an example of a rate of change in the COVID-19 pandemic? Well, as time goes on, right? As time goes on, so if I put time on this axis, right? As time increases, what happens to the proliferation of the virus, right? So the virus, how common is the virus among the population? Time moves on, maybe the amount of spread of the virus increases. And that was a concern towards the beginning of the pandemic, right? When they shut down services and the economy and things like that, because they're very, very concerned that the more people out there, spreading the virus, it's going to actually continue to grow very, very fast. And they were even concerned that it would the rate of growth would even be steeper than this. And oftentimes those rates of growth follow an exponential curve like this. See, this exponential curve, if you have a little bit of change here, well, at first it doesn't produce that much of a change on the y-axis. But as you have more and more time and proliferation of the virus, well, then it increases at a faster rate here. So these types of changes were very, very concerning at the beginning of the pandemic, which is why things were shut down a little bit. And we're hoping that when they say we want to get over that curve, we're hoping now that we're starting to slow things down. So science is all about rates of change. Now, if I have more than one x variable, right? So maybe I have x1 and I have x2, not just that one x. Recall up there we only had bx. But what if I have an x1 plus an x2? Well, then I'll have a b1 and a b2. So I'll have one x1 here and an x2 here, and then I have my y. So we can have more complicated linear equations here. It doesn't only have to have one b and one x. We can have one axis here, another axis here, and so on. And this forms the basis of a technique called multiple regression. Okay, multiple regression uses several x's to make a prediction of y. So we're interested in the rate of change of y for given values of x1 and x2. And multiple regression is something we're not going to only get to the end of the course. We'll talk about it a little bit, but you see that all of the statistics we're going to learn are based on these concepts. There's the linear equation right here that we just talked about, where we have x1 and x2. You can have different shapes of equations. So there's the linear equation we've been talking about. Here's a quadratic equation, right? Quadratic equation has that particular shape. It's a parabola. So different forms, different polynomials, right? There's to the 3, that's cubic. So a whole bunch of different forms. And We can continue going up in numbers here. We don't have to stop at 3. We can go 4, 5, 6, 7, 8, 9. We can keep going higher, and then the curves become pretty complex. Usually for the purposes of scientific investigation, you don't want to make that complex of a curve, right? And many statistical methods are based on this. There's entire books based on statistical methods applied to linear equations like this. But in more complicated things, you may want to consider different types of curves. Well, when we look at polynomials, okay, polynomials are functions of this particular form. So we just looked at some polynomials up there where you're increasing the value of the exponent. So these are all the equations we just talked about, the quadratic equation, like that, the cubic equation, and that polynomial can have different orders to it, okay? For our purposes for statistics, we're really interested in polynomials because they're going to describe that shape of the change, right? If you look at the quadratic again for a second. Well, if I have a change in x and then a change in y, triangle y, well, what happens as x increases? What happens to y? Right? Notice as x increases, y decreases, right? I'm having a decrease until you get to the bottom. And then what happens? It increases. Okay. Now, one good example of a quadratic shape like that, and you may have heard of it from intro psych class or another class, is the inverted U. Okay, what's the inverted U curve? Well, if I have, say, like test performance, that's PERF, performance, and over here, I have anxiety. Okay, anxiety, or you can even think of that as energy, you know, the kind of amount of attention you're giving to the test, right? Anxiety is a good word because you come into the test, you're kind of ready for it. You got to have a certain amount of arousal, right? That anxious arousal. If you come into the test, you know, if this is the test performance and you come into the test and you're asleep, well, you're not going to do well, right? So if you have a low amount of arousal or anxiety, your test performance is really low, right? You got the 0 over here because you have 0 energy. But what happens as your energy increases? Well, as your energy increases, maybe you do better on the test because you're more alert, right? That energy drink, all those energy drinks, boy, we shouldn't have too much of those because I think those can be a little bit dangerous if you have too much. But if you have an energy drink before the test, your performance increases, your energy increases until your performance is optimal, right? Your performance is optimal. But what happens when you have that second energy drink, right? You have the second Red Bull or whatever those things are called right now. What happens? Well, you don't want to have too much, or you don't want to be too anxious, because then what? Your performance is going to drop, right? You can't come into the test filled with anxiety because you're just not going to be able to do well on the test. That's the idea of the inverted U, right? Inverted U curve. It's the Yerkes-Dodson inverted U. Again, you don't have to memorize that. You know, you're not memorizing what I just said. You're just understanding it and acknowledging that it makes good sense, because that type of knowledge is going to pay dividends when we look at other things in the course. So you notice we're interested in rates of change. I'm going to skip over logarithms and exponentials. Interesting stuff. You probably have computed some logs before, but we're going to skip over that stuff. Now, there's a discussion of limits here, and the best way to understand what limits are is to look at a graph. So we are almost to the topic of calculus. We're almost there, because when we get into limits, limits are the basis of what calculus is about. So let's just study this graph a little bit and kind of see if we can make some sense of it. We see that this graph, okay, so we've plotted a curve here. We've plotted a curve. We have our x axis here, and we have our y axis here. Now, this notation requires some explanation, the f at x. When we talk about a function in mathematics, okay, that is a function. What we mean is that when you input a value for x, what happens to y? Okay, what happens to y? So this notation here is read the function at x. In other words, what's the value of y for different values of x? Okay, that's what we mean by the function. There's other particulars about functions that we could study if we had more time to do this, but this is the central idea of the function. When I put in a value for x, one value here, one value here, notice that I'm getting a different value for y, right? I'm getting a different value for y. I'm not getting the same value for y. I'm getting a different value. So for different values of x, I should be getting different values of y. If that were not true, if I were able to get more than a single value for y for a given value of x, then I don't have a function. Give an example of something that is not a function. Circle. There's x, there's y. Look at that value for x. How many values of y can I get from that? I get this one, and I get this one, right? It's not a function, because for a given input of x, I get more than a single value for y. This graph, on the other hand, looks like a function, because it doesn't look anything like that. For given value of x, I get different value of y, right? This value, I get this one, I get this one, and so on. So let's talk about the nature of this curve. Okay, the nature of this curve is a continuous curve. So we see that the curve is continuous. Okay, that says continuous. Now, what do we mean by continuous? Well, we're going to talk about continuity when we get in the book, but you're going to see that the book doesn't treat continuity at the depth that we're talking about it. We know what continuity is on an intuitive level. Nobody needs to tell us that. Look, this is a continuous line, right? Why? Why is that continuous? Well, that's continuous because I didn't lift my pen off the page. I just continuously drew. It's a continuous line. Here's an example of a non-continuous line, right? Notice the space. That's a non-continuous line. So continuity, we know intuitively, just means keep your pen on the page and draw. We have a continuous curve. This curve is continuous. But informal definitions like this don't really suffice. We want to be able to talk about these things in a little bit more defined terms. And that's exactly what a lot of mathematics does, is it takes concepts like this and it defines them more rigorously. Okay, it invents notation for them and it makes it very, very precise. So when you look at all of this complexity here, you're looking at mathematics rigorizing concepts, right? It rigorizes things like this, and it does so in a lot of detail. Let's look at what's going on here so we can get to the definition of a limit. And again, limits you may have heard of in high school, and you may have computed limits, but you may not have understood what a limit actually is. Well, look at this continuous curve. I'm going to define an x sub 0 value right here. Okay, that is a value on the x-axis. Now I'm going to define some space around that x value, and that space around the x value, I'm going to denote the change by delta. That's a delta sign. So I've defined a little bit of space above x and a little bit of space below x. X sub naught, that means x sub 0, x sub naught plus some change, x sub naught minus some change. So there's a little bit of space here. Well, what happens on the y-axis when I define some space over here? I'm also going to define some space over here. So if this is the value here on the y-axis, I'm going to have a corresponding epsilon value. That's the little e, that's epsilon. So I have this L, which we'll define in a second, plus some epsilon, this L minus epsilon, right? So what you're seeing here is as we make a little bit of a change in x, we also have that corresponding change in y. As I narrow in toward x sub 0, right? Imagine I reduce this distance here to less and less and less and less and less. What do I eventually get? I get towards x sub naught, right? So as I narrow in the neighborhood around x sub 0, what's the neighborhood? It's just that distance around x sub 0. That's all that is. That's x sub 0 minus delta, x sub 0 plus delta. That's what we're calling the neighborhood. What happens over here? Well, I narrow in towards this value. Okay. Again, the concept here is very, very simple. The notation looks a little bit complicated, but the concept is simple. Narrow in over here on x sub 0, you're narrowing in over here on this value. Well, what is this L called? Okay. We're going to say the limit of the function f at x as x approaches x sub naught is L. This is a key definition of calculus. Again, you may have computed limits before, but you didn't understand maybe what they were. So as x approaches x sub naught, as we zero in towards x sub naught, the limit of the function, what's the function? The function is f at x, right? This is the nature of this particular function. The limit of the function is L. That is called the limit over here. That's what L is. And this idea of limit also pertains to helping to define the continuity of the curve. Because we see if this curve is continuous, then what should be the case is as we zero in on x sub 0, we should be zeroing in on that number over here, right? You can see that it's helping us get a grasp of how continuity can be conceived in mathematics, okay? The gap in the curve above x sub naught is meant to suggest that the function is undefined at x sub 0. Now, what this means is, well, this is an idea that the author of these notes talks about that it's a little bit more than we need to go, but it just says that the limit can exist even if this point is not necessarily defined. So x sub 0 does not necessarily even need to be defined. And you see this little gap here? In this case, x sub 0 is not defined, but the limit can still exist, even at an undefined point, because we actually don't care what's happening at the point, we care about what's happening near the point. So let me just redraw this over here, x and y. As we get closer and closer to x sub naught, where does the function go? That x sub naught value does not necessarily even need to be defined. And that's what that space means over here. We can still talk about the limit, okay? Okay, so that's a look at limits, and limits are used in calculus. There's some rules for manipulating limits. We don't have to know that. It just says how to do math with limits, but for now, it's the concept that's most important. Here's an example of that undefined idea. The function is undefined at x equals 1. Now, if you look at this function right here, right, this function, look at that denominator. So let me just put it back up here. I have x minus 1 equals 2. This is the limit of the function. The limit as x goes towards 1 is equal to 2. Well, the reason why the notes say that it's undefined at x equals 1 is because if I put a 1 here, right? If I put a 1, if I let x equals 1, what does our denominator equal to? So that's 1 minus 1 is equal to what? 0. So my numerator, if I take my numerator and divide it by 0, that means it's undefined. Right? If you try doing that on your calculator, if you take a number and divide it by 0, you're going to get something like that big E message. And that's saying, basically, it's saying I can't compute it, it's undefined. So we see that even though the function is undefined at x equals 1, it means you cannot put a 1 there and make things work. It's undefined. The limit is still equal to 2. So it's undefined, but the limit still exists. So this idea here that you have an x value and you have a limiting value over here, it can still be the case that it's undefined. Now, some cases it won't be undefined. In most cases, it won't be undefined. But it's just the idea is we're interested in what happens as we get closer and closer to x. But we do not necessarily need to be at x. And in this case, we cannot be at x equals 1. So when we think about limits, we're thinking about what happens over here as we get closer and closer to the value. Okay. Again, that's probably a little bit more than we need to know, but you just should know that when you talk about limits, it's where is it going rather than where it ends up as. Because if it ends up at 1, the function kind of blows up, right? We can't compute it because it's undefined. Yet the limit still exists at that particular value. Okay. Okay. So that's a little bit about limits. Now we need to talk about derivatives. We're going to get into this for the next, about 3 minutes, and we're going to continue on Friday. We'll finish it up. Let me just give a little bit of motivation for where we're going here. Here we have x, and here we have y. Well, I have two values here. I have x1 and I have x2. Over here, I have y1 and I have y2. Now, when we're looking at things like this, I have a curve, right? I have a curve. Well, imagine I wanted to change these values so I have a change in x, right? I can, first of all, draw a slope joining these 2 points over here, right? So I've just drawn a line that connects 2 points of this curve. But notice that I can also bring x1 in and x2 in. So what happens as x1 comes in and x2 comes in? So in other words, what happens as the change in x gets smaller and smaller and smaller? So what does that look like on the graph? Well, for that change to get smaller and smaller, what has to happen here? This has to go this way, this goes this way, this goes this way, and eventually I'm going to get this change corresponding exactly to what's over here. So if I were to bring these lines in, what would I do? I draw another line, and I draw another line, and that's exactly what our author does over here. Draws a whole bunch of lines right stemming from this particular location. Okay. Now, over here, I drew this line connecting this point, but we actually want to keep this point stationary. We want to keep that fixed. Because if I draw this point and this point, then I'm getting another line. Let's instead try keeping this point fixed and simply changing this one. Well, if I do that, I'm going to get what is pictured over here. Notice that I'm drawing a whole bunch of different lines, and as I bring x2 towards x1, I'm kind of zeroing in on this spot over here. Now this x2 moving towards x1, what this is illustrating is that the change in x is going to what value? What value is it going towards? Right? It's going towards 0. Right? The change in x is moving towards 0. x2 gets closer and closer and closer and closer and closer to x1. That's the concept we are looking at over here. As this change goes towards 0, how can we discuss this particular slope, right? You get another line, another line, another line, until we want the exact slope at this particular point. What is the slope at this particular point? This is what we need to determine. We know what this slope is. Go back to this graph. We can compute this slope, right? We can compute the slope between these 2 points. If I connected another 2 points in here, we can compute that particular slope. If I connected these points, we can compute that particular slope. But as I do what's being done in this diagram, as I bring one value of x2 closer and closer to the other value, how are we going to talk about that particular slope right here? To talk about that, we are going to need to develop the concept of the derivative, okay? And that's what we're going to talk about next time. And we're going to see that the derivative is going to use the limit concept that we've already developed, because what the derivative wants to do is tell us what is the slope at that particular point as the change goes to 0, okay? Okay, so that's it for today. We will finish this up on Friday. Again, I want to highlight, you're not memorizing it, all of this. You're looking at it, you're understanding it as much as you can of what you're looking at. If you've never seen calculus before, all of this stuff is, may come across as, wow, this is a lot of stuff to take in. Don't worry too much about it. We're just doing a little bit of precursor stuff before we get into the book. Just see if these ideas click with you a little bit, okay? You're not memorizing it. You're just getting a feel for what these concepts are about, okay? They're not going to be tested rigorously on the test. When we start in with the actual book next week, that's where you'll have a little bit more clarity on what you need to know exactly. We're just doing a bit of a precursor to getting into the book. But if you've seen some of this stuff before, these calculus concepts, and you've computed some calculus, you should be familiar with these a little bit. And if it's new to you, well, this is your first look at these ideas. And if you do plan on going into statistics more, you'll definitely see these things again down the road. Okay, so that's it for today. And we are going to continue on Friday, and then we will be into the book.